Okay, I'm going to talk a little bit about what is, I guess, a new activity for the ERC. It's an activity in interconnection and demonstration. My own background, as Paul has introduced me there, is in power electronics. So a lot of what I'm talking about here, I'm taking from the sort of power electronics side of things. As I said, it's a new activity, so I'm not going to be presenting any results here today. Mostly what I have in my presentation are just questions, so no answers yet, but hopefully in the future we'll come back and have some answers. As a new activity, we have a few people just recently started. We have Roland Muir as a postdoc who's looking at high voltage DC connected wind farms. Roland has a poster out there, so you can see that later. We also have Murren Lynch, who's been doing a PhD here for some time under Mark, looking at techno-economic aspects of interconnection. I also have a recently started PhD student looking at power electronics transformers. We're hoping to expand that number of people in the coming months, hoping to hire one more postdoc and 2 more PhDs in the coming months. So what I want to, I suppose, bring you through here today is a little bit of the motivation behind why we're starting this activity in interconnection, why it's important, and then I'll move on a little bit to explaining perhaps some of the areas which I think are relevant to have some research in. And following me will be a presentation from Mark Norton from EirGrid, who will talk a little bit about the studies that EirGrid have done in offshore grids. So first of all, the background. Why interconnection? Why is it important? Well, I guess most people know about the Europe 2020 targets. And even if you look beyond 2020, there's the notion that by 2050, maybe perhaps there should be an 80% greenhouse gas reduction, which implies an almost zero carbon power supply. So the background to all this is really how do you achieve that very significant level of renewable energy integration into the system. Most studies, and I guess the graphic I have here just shows for that sort of 80% greenhouse gas reduction target. You can see the graphic here sort of shows how that might be achieved in terms of the technologies used. So there is, it's a graph of the demand over the year for 3 different scenarios showing the various technologies that might be used in order to achieve that 80% greenhouse gas reduction. And as you can see, there in the middle, there's a huge emphasis on wind and photovoltaic, wind in the blue colour, photovoltaic in the sort of orange colour. And also one thing to note there is the complementarity between the wind and the photovoltaic. So during the summer months there, when the wind is quite low, the photovoltaic, the energy from photovoltaic is high, I guess because the sun does shine in some parts of Europe during the summer. So what most studies which look at this notion of trying to integrate so much renewables into the system, most studies come to the conclusion that the need for an expanded and interconnected European grid is hugely important. Why is that? Well, the obvious and simple reason behind it is the notion that you can transport the renewable energy from areas of high concentration to areas where it's most needed. So to do that, you need an expanded grid which will interconnect the different countries in Europe. There are also other benefits, not just simply the moving around of the renewable energy from one area to another. If you think about it, it facilitates sharing of reserves between the various countries. So typically renewable energy, if you're trying to integrate renewable energy into the system, it requires a high level of reserves to deal with the uncertainty of that renewable energy. If you interconnect over a wide area, you can facilitate sharing of those reserves and an overall reduction in the backup generation capacity required. Some studies estimate that by as much as 30 to 40%. There's also an effect, which I'll show in the next slide, but reducing the demand variability when the demand is aggregated over a wide area. It also reduces the volatility of wind. So the wind may be blowing in some places at certain times and not in others, but if you can interconnect everything and aggregate it, then you can overall reduce the volatility associated with that wind. And also, as I highlighted in the previous slide, there's this notion of exploiting this negative seasonal correlation between wind and solar. Just to highlight a little more on that reduction in demand variability, here's a graphic which is taken from the European Climate Foundation report, which looks at, it tries to quantify by how much you could reduce the demand variability if you were to interconnect over a wide area in Europe. And the point is, what the graphics show really is the variations from the average of the demand over a day and over a year. And what you can see is the solid line there represents the aggregated demand, and its variations from the average are much lower than a lot of the variations from the average on the individual lines, which are the lines for the individual countries. So there's this notion that interconnection, a high level of European interconnection, can reduce demand variability. Of course, that idea is quite interesting, but the question is, does it make economic sense? What does it cost? There's been a study done here in UCD on trying to look at the cost of building such interconnection. And this study really, it tried to ask the question, if you look at the demand going forward, and you ask, and it took as an example in this case, a case study of 8 Northern European countries. If you look at the demand going forward, how can that demand, and allow that demand to be met by either building interconnection between countries or building actual generation capacity? And you constrain that by the fact that there are renewable targets, and it compared individual region targets versus global targets. And the overall objective of this study was to minimize costs. And this is just a sort of a sample of some of the results from that study. What it concluded was that there is a reduction in costs from building interconnection, but only if the renewable targets exist. So that if the renewable targets don't exist, there was the optimization program would not have chosen to build interconnection. It just simply chooses to build generation. There is an overall cost reduction if the renewable targets exist. The graphics here, the one on the right shows a percentage reduction in costs depending on different factors in the simulation, like wind integration cost and discount rate. But I suppose the thing is, that reduction in costs is achieved by a reduction in the building of generation capacity. And the graphic on the left shows the percentage reduction in thermal generation capacity that will be built if the interconnection is built. So I guess the point of the study is to sort of show there is some sort of economic benefit to this notion of building a European level interconnection, which is sometimes referred to as the European supergrid. Offshore wind has a very significant role to play in achieving European renewable energy targets. And indeed, if you look over the projections for the coming years, so currently offshore wind is actually a very small part of the total wind generation. It's currently only about 5 gigawatts installed Europe-wide. By 2020, it's estimated that'll increase to about 40 gigawatts. By 2030, 150 gigawatts. So offshore wind has a very significant role to play in meeting renewable energy targets. And if you look down, and this is the graphic shows the predicted builds in offshore wind for the various countries. And you can see Ireland down there in the middle, and it's not an insignificant amount of offshore wind predicted to be built in Irish waters, about 4 gigawatts. Offshore wind, of course, integrating offshore wind implies that there has to be some sort of offshore grid infrastructure to interconnect that. I'm not going to talk in any great detail about that. The talk from Mark from EirGrid following me will talk about their studies in the bill in looking at offshore grids. Okay, so that's a little of the background and hopefully conveys why it's important to look at this area of interconnection. The next question for me starting was, well, what are the sort of interesting research directions here? So from a technical perspective, a large portion of that European supergrid, if you will, is going to be based on high voltage DC technology. Why? Because it really involves the interconnection of asynchronous systems, so systems which are not operating synchronously. It involves the transport of large bulk power over long distances. DC is a lower loss alternative for doing that compared to AC. And also something which high voltage DC brings to the whole picture is controllability. So if you think about it, what high voltage DC, how it works is basically you transform the AC into DC using a power electronics converter, transmit the DC over cables or overhead lines depending on the situation, and then transform the DC back into AC again using a converter, a power electronics converter. Those power electronics converters offer the key to the controllability. However, it also offers lots of new challenges in terms of how exactly you might control the power flow in mixed AC and DC systems, and also what's envisaged. What is envisaged is a meshed DC system, which brings the notion of multi-terminal DC. And I'll talk a little bit about that in the next slides. So essentially the point is the power electronics here are the enabler for this sort of interconnection. And power electronics brings benefits, as I talked about, the controllability, the intelligence, decoupling, so decoupling sort of the mechanical side of generation from the electrical side. However, power electronics also has drawbacks, so it's higher loss typically, it's got harmonics associated with it which have effects on the system, there's question marks over reliability, and of course costs. So I think all the studies in looking at the interconnection have to be framed in terms of that, trying to achieve that balance between the benefits and the drawbacks. As I said, there are some studies been looking at suggesting how such a European-wide interconnection might be built. It looks at various things. So one simple way here at the top, it shows it's just a simple DC, HVDC backbone overlaid on an AC grid. That, however, with just a single point-to-point connection like that, doesn't offer any of the benefits associated with a meshed grid. So it's more likely that there would be some sort of meshed grid scenario, which is the bottom two. The middle scenario there is where you might construct the grid from independent DC lines. The bottom scenario is a truly meshed system with a common DC voltage. So that brings a lot of issues in terms of a lot of questions around how you control such a system. In particular, most existing HVDC is point-to-point. What I showed in the previous slide was that it's envisaged that any system would be a mesh system, so a multi-terminal system. So there isn't much experience in existence on how to control and operate multi-terminal HVDC systems. There's also this question of there are different HVDC technologies out there. There's what's called the classic HVDC technology based on thyristors, and the more modern voltage source converter technology based on IGBTs. Any system would have to consist probably practically of a mix of those because of the large installed base. So there's questions around how you control it with such a mix of technology. There's also a lot of questions around, I mean, the control in such a grid can be envisaged at different levels. There's a very high level control which simply responds perhaps to the market that says how much power is needed in various nodes on the grid. Then there's a low level control at the level of the actual power converters who have the responsibility of perhaps maintaining voltage regulation, power regulation, etc. But in the middle between those, there's a whole lot of very interesting research, I think, to be done in how system support can best be provided by such a grid and such power electronics converter-based HVDC stations. So things like reactive power and voltage support, frequency support and simulated inertia, power oscillation, damping, etc. So lots of interesting, I think, research questions to look at there, which have really only been touched on to date. Another aspect, just to come back to the offshore wind aspect again, and power electronics. So power electronics, I guess, okay, I should say offshore wind is driven, I suppose, largely by concerns of reliability and maintenance. Power electronics, I think, has the, can enable different sort of configurations in offshore wind farms. However, they're also part of the problem. And this graphic here shows, it's a collection of reliability data taken from 1,500 wind farms over years. And basically, it shows the annual failure rate of various parts of the wind turbines on the top, and the number of down days attributable to those on the bottom. And you can see that the electrical components there actually have the highest annual failure rate. However, on the other side, they actually contribute to the smallest downtime. So really, the power electronics, although they fail, they're relatively easy to replace. But the point is, I guess, the power electronics raise reliability concerns. So one of the things we've started to look at here is different configurations for offshore wind farms, which might minimize the power electronics, minimize the power electronics configurations and converters used in them. So what I'm showing here is, I suppose, a more conventional approach to a wind farm, where you have a series of individual turbines, each with their own converter, which does the control of optimizing the power output. What we're looking at here, what the postdoc Ronan Mears is beginning to look at, and he has a poster outside on it, is how might you reconfigure that, perhaps so that a cluster of wind turbines is controlled from a single high voltage DC converter, and so you can eliminate the converters, the individual converters in the turbines. Another interesting aspect of this is the role of DC-DC conversion in any DC grid. So obviously, if it's a DC grid, transformers don't work anymore, so you have to have some sort of DC-DC conversion integrated into it. That's another aspect we're looking at. We have a PhD starting looking at power electronics transformers. Just finally, to end up, I didn't talk a lot about the demonstration aspect of this, but one of the pieces of equipment which we're currently acquiring in the ERC is something called a real-time digital simulator. And really what this allows is the capability to do what's called hardware-in-the-loop real-time digital simulation. So really, basically what it allows you to do is to run a simulation of the grid on the computer and connect that up to real hardware, so that you can study the interaction between the hardware and the simulated version of the grid. I'm just going to finish with an example of the kind of thing that sort of thing does. This is an example taken from a European project called 20s, where they were looking at DC grids, and they simulated so all the parts in the light blue there are simulations. The parts outside of that is actual hardware. So they were able to simulate the grid and the controls within the real-time digital simulator, connect that up to real hardware, which is, in this case, a collection of DC cables, and see how the interaction of the system works. So basically, I guess it allows you to test controls and real hardware without actually going to the full grid test.